Okay, so I want to pick up from where we left off. We talked about the three rules when it comes to electron configuration. There's a few things that kind of throw a wrench into the way this works that they don't work as expected. Plus, I want to go through how to actually do this now. So first, I want to start with the things that kind of make it a little bit weirder. And those are, in particular, the D and F subshells and energy levels in general. So I was very, very specific, and I said it a couple of times when I mentioned the Aufbau principle. The electrons will want to fill the lowest energy orbitals first. So not the lowest energy level, but the lowest energy sublevels and orbitals. And I state this because when it comes to the D and F sublevels, energy and energy levels start to kind of get a little wonky in terms of where they are compared to others. So, after energy level 3, or after subshell 3p, d orbitals begin appearing. And then starting after 6s, F sublevels start appearing. So energy level 3, we start seeing d orbitals. Energy level 4, we start seeing F orbitals. Now, you may be thinking that, well, I just said two completely different things, because I said after 6s and after 5p, but then I said energy levels 3 and 4. Well, this here is why it gets kind of weird, and this is why I specified subshell, not energy level. If we look at this diagram, and I showed you guys something kind of similar in class, going from the bottom to the top is the increase in energy. So our 1s subshell, all the way at the bottom in yellow, would be our lowest. Our 6p subshell, all the way at the top in light blue, would be our highest. Some of you picked this out in class, and some of you might have already noticed it, but the principal energy level, so that number that goes in front, the principal energy level, does not fit with what the actual energy of the subshell is. So we can kind of see these jumps going from, especially for S and P, going from S to P, there is this relatively small jump. And that jump does get bigger as we go higher and higher and higher into the subshells. But once we hit subshell, or once we hit energy level 3, we would expect, okay, if I'm going to keep filling energy level 3, I'd go 3s, 3p, and then 3d, right? But as we can see, our 4s sublevel, 4s is actually lower energy than the 3d sublevel. Same goes for 5s compared to 4d, and even 6s compared to 4f and 5d. So in terms of energy level, there is this kind of relative level for each one. And I tried to draw these lines as straight as possible. I'm pretty sure I got them pretty straight. And you can see that 4s compared to 3d is actually lower. So that is the subshell that we would start with going from 3p. We'd go from 3s to 3p to 4s to 3d and then to 4p. And same as we continue up. And as we go through, as these atoms get bigger and bigger and bigger, and the configurations themselves get larger and larger and larger, they will have these more bizarre jumps in energy. And we just kind of have to be cognizant of that. So, like I said, even though it is the D energy shell, the D sublevel for energy level 3, it has a lower energy, or it has 4s has a lower energy than 3d. So moving on then. We've talked about the rules of electron configuration. Now, I want to talk about the configuration in reference to, or in relation to, the periodic table. In short, as atoms grow, as they get bigger and bigger and bigger, we simply add an electron to the shell. So every time an atom gets bigger, it's going to gain a proton, it's going to gain some number of neutrons, and it's going to gain an electron. There are several other trends relating to electron configuration and the reason why the periodic table is shaped the way that it is. But for now, we will only be focusing on atoms getting progressively more electrons, because that's what we're looking at right now. We're looking at the configuration and building these bigger atoms. So what I mean, for instance, when I say getting bigger or getting progressively larger, first thing I want you to do is I want you to get out your periodic table. So I'll give you a second. Okay. Starting from hydrogen, because hydrogen is our smallest atom. So going from hydrogen to helium, and then from helium to lithium, and so on and so on and so on, going left to right, top to bottom on the periodic table, the atoms are going to be getting progressively more electrons. They get bigger, they gain particles, etc., etc. As they fill, as the rules above, or as the rules from earlier mentioned, as they get bigger, as those shells get full, we'll move on to the next sublevel or the next energy level to continue going and going and going. As more and more electrons fill these atoms, they fall into place based off of those three rules from earlier. Remember, this is based on which one would have the lowest energy, as stated before, not the lowest energy level. So those D and F suborbitals kind of throw a little bit of a wrench into the situation. Just make sure that you are aware of it. And once again, for example, we fill 4s first, and then we go to 3d. Or we fill 6s first, and then we go to 4f. Like I said, the shape of the periodic table is based on several things. There's a few things that kind of lend themselves to the way that it's prepared. But there is a major reason as to why it has kind of that weird shape that it does. And we're going to continue that on the next slide. So on the next slide, I do want you to have your periodic table out. That way you can identify these particular blocks as we go through. So what I want you to do is, I'm going to pause for a second. I want you to label, identify, color, whatever you need to do to identify which block is which. Because these are the atoms in the given areas that will have electrons getting added to those spots. So I will pause the video and give you a second. Okay. So I'm going to go from section to section. There are 4 sections corresponding to the 4 types of subshells: S, P, D, and F. First is our S block elements. We call them S block. These are the first 2 columns on your periodic table. And helium. So helium and hydrogen kind of have a weird spot. We sort of consider them, they can fit on both, either at the top of the S block or at the top of the P block. They fill an S suborbital, so we consider them S block elements. But we will go more into their weird placements next unit. So these are the atoms, and as you can see, there's 2 for each one, because only 2 electrons fit for each S orbital. Those first 2 columns are S. Next is the P block, which is labeled in orange. The P block is a group of 6 columns. Once again, P block can hold 6 electrons. So this goes from, these are the 6 furthest right columns. And these are the groups that have boron, carbon, nitrogen, oxygen, fluorine, and neon at the top of those columns. And once again, we're excluding helium because helium is actually S block. Okay? So continuing on then. Next is our D block. D block is that blue section right in the middle. These are the groups that they fill the D orbitals. So there's 10 elements, 10 columns here that kind of fit this group. And these are the 10, starting with the column that has scandium at the top and ending with the column that has zinc at the top. So going, once again, left to right, starting with scandium, ending with zinc. That is the D block. Lastly is the F block elements. F block are the ones that are kind of set below the periodic table. They are listed in this weird spot, and we'll look at why, once again, next unit. These are the bottom 2 rows, the ones that are separated from the rest of the periodic table. Before you label these, I do want to clarify one thing. If you count, there's actually 15 elements there. The 2 elements, so I want you to pay attention to the elements I mentioned. The actual F block elements go from number 58, cerium, through number 71, lutetium, and from number 90, thorium, all the way through number 103, lawrencium. We call these 2 groups, we call them lanthanides, actinides, because lanthanum, number 57, and actinium, number 89, those are what we use as kind of like the first 2 elements for each of those rows. But those 2 elements I mentioned, once again, lanthanum, number 57, and actinium, number 89, those are actually D block. So the way that these fill is they actually start with a D electron and then go into F and then continue with D for their respective rows. I know it's weird, but as always with science, it's whatever the evidence shows. And we're actually not really going to be doing a lot with elements that are that big. Okay, so we don't really need to worry about them aside from being able to identify them based off their configuration. So, moving on. How to write electron configuration. So this slide and the next one, I'm going to give you the order, and then I'm going to give you an actual chart that goes with it. So, to write electron configuration, so not just draw it with the arrows like we have been doing, we can actually do this just by writing out just like we did with the manager's code and the electron configuration in the packet. What energy level, what subshell, so what energy level, what subshell, how many electrons are in that subshell, and we just continue on and on and on and on until we're full. So a couple things we need to remember is, number 1, how many electrons can each subshell hold? S can hold 2, P can hold 6, D can hold 10, F can hold 14. And we have to remember the order of energy from lowest to highest. You're not always going to have a chart, but I am going to at least walk through the order of these. And like I said, I'm not going to give you any huge elements that you'll have to deal with. So, as I said earlier, electrons will fill the subshells and the orbitals of an atom as they are added, making that atom progressively bigger and bigger and bigger. As a reminder, electrons will settle in the lowest shells first. So they'll settle in where they are most comfortable. They will only pair in a subshell when every orbital in the subshell already has one. And they will only pair with opposite spins. Don't forget those rules. As we moved, once again, for the periodic table, we go from left to right, top to bottom. There are more electrons added because there are more protons. The particles themselves are just continually being added and added and added. They will fill the orbits in this order. Now, like I said, I'm going to pause after this. Okay? So, the orbits, starting with 1s, because that's our lowest. So, the electron configuration I'm giving you right now is for element number 118. This is the biggest element that we've discovered. It is a synthetic element, highly radioactive, doesn't really exist very long. But this is the electron configuration that it has. Lowest orbital, 1s. So 1s2, and then 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, and 7p6. Like I said, I want you to copy this into your notes. Second is this diagram. Once again, I'm not going to talk about this too long, but I want you to copy this in your notes. Same thing, going from lowest energy to highest. And this is the way it's laid out. All you do is you follow the arrows. Once you get to the end of the arrow, you start at the next one. So 1s, 1s2, then 2s2, 2p6, 3s2, on and on and on and on. So I want you guys to stop and copy this in your notes. Alrighty then. Now I have a question for you. Now that we've gone through all this, what I want you to do is I want you to write the electron configuration for the element selenium. So I want you to find selenium on your periodic table, and I want you to write the electron configuration for it. Okay. What you should have written is this. For selenium, selenium's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. So notice, I did not go all the way to 4p6 because there aren't 6 electrons in that p orbital yet. You only add the number of electrons that you need to fill out the atom, right? So there's going to be 2 missing electrons from selenium. So it will end at 4p4. Last thing I want to talk about here before we wrap up. These electron configurations are fantastic for identifying elements, but they can get very unwieldy very quickly. They get very difficult to write. There's a reason why I'm not going to have you write any of the big ones. Because due to the size of some of the atoms that scientists work with, or some of the ones that they create in a lab, that's a lot of stuff to write. So, we have a shorthand for this. It is called the noble gas configuration. The way this works is we start with the previous noble gas, which is the column that is noble gases is column number 18, the far right column. So, as opposed to writing the full configuration, we start with the previous element from row 18. Then, continue the configuration like normal. So, for example, the one that we did on that last question, selenium. Selenium, its configuration, as we said, is shown. The way that we would write this is if you look, the previous noble gas, so from the row that's right above where selenium is, the last noble gas was argon. So we would put in brackets Ar for argon, and then we just pick up where we left off. So argon, 4s2, 3d10, 4p4. And I know that this is the configuration of some atom after argon. And I can count, okay, there's my 2 for the P block, there's my 10 for the D block, which means I'm 4 into the next P block. Okay? It saves time, it's much easier to do, and it's much easier to identify. So to wrap up, I just have one last question, and then we're good. What element does this electron configuration represent? So now I'm giving you the electron configuration. Tell me what atom it is, what element it is, and then I want you to write the noble gas configuration for this element. And you don't need to use superscripts for this. You can just put 1s2, for instance. Okay. So the element that you should have come up with is zirconium. This is zirconium. To write out zirconium, which is one of our D block elements, we would start with our previous noble gas, krypton, Kr. Then it would be 5s2, 4d2, because it's only 2 into that D block. All right. So, excellent job. This is where we'll wrap up. And I'll see you guys soon.